All right, I was looking for a video, but I think I just want to show you guys this myself. So we were talking about rate laws. So if you'll remember, we have a generic equation for the rate law itself, which is that the rate is equal to a rate constant, which we don't know yet, times the concentration of both of our reactants. So in this case, we're given the chemical reaction, which is going to have our fluoride raised to some exponent that we also don't know yet, times our second reactant. So as we do this then, we want to be able to solve for these exponents. The tricky thing is there are multiple ways to do this. So what I'm going to do is go ahead and show you two different ways to solve for these. There are actually more than two ways to solve for these. As you may have already witnessed in this course, problem solving is a major component, which means there's usually more than one option to do these. So when we're looking at the fluorine, what we're going to be doing is looking at these experiments. So I have a data table up here. These are just the experiment numbers. Then I have concentrations of my fluorine, concentration of a chloride compound, and the initial rate that goes with it. So in looking at how in the exponent I'm going to need for my fluorine, what I'm going to do is I need to compare two experiments where the thing I'm looking for changes, but nothing else. So I'm going to use definitely this third experiment, and I'm going to use either this first one or the second one. The thing that's going to let me know if I want experiment 1 or 2 is by taking a look at this other reactant. So you can see that if I chose experiment 2, I would have both things changing at the same time. That's not a good way to figure out what's going on. So what I'm going to do is I want to make sure that only one thing changes. So I'm going to choose for this experiment 1 and experiment 3 so that I have my fluorine changing but nothing else. So the first way I'm going to do this is what is usually the kind of logic-y way, which some people love and some people don't. To do this, really what we're looking at is we're looking at the relationships of these numbers. So as you look, when you go from experiment 1 to experiment 3, the reaction concentration is doubling. So we have twice as much of my fluorine when we go from experiment 1 to experiment 3. And then when we look at the initial rates, we also see a doubling of the rate from experiment 1 to experiment 3. Now, if you really wanted the hardcore numbers on that, you could go ahead and divide one by the other. So we could look at my fluorine and say, I have 0.2 in one case, I have 0.1 in the other, that gets me number 2 for the doubling. When I look at my rate, I can do the same math and take a look at my 2.4 times to the negative 3 and divide it by 1.2 times to the negative 3, and that also doubles. The fact that you get the same number, no matter what this number is, the fact that it is the same tells you that this is a linear relationship. So since it has the same factor, it's a linear relationship. This is going to have, therefore, an exponent of 1. So again, some people like this, some people don't. So let's go ahead now and take a look at the other thing, this chloride compound, and as we do that, we're going to use a different method. So we still have to pick our equations. In picking our equations now, I want something where my chloride compound changes, but my fluorine does not. So I want these first two. So my fluoride's all the same, my chloride changes. So I'm going to pick experiment 1 and experiment 2. Now what I'm going to do is I am basically going to plug in to this equation. We know that this is the generic form of the rate law. So what I can do then is I can go ahead and say, I know all of these wonderful things, but I'm going to use a ratio so I can cancel some terms. Let me show you what I mean. So we are going to use experiment 2 and we're going to use experiment 1. In using experiment 1 and 2 then, I'm going to fill in the blanks. So I have a rate for experiment 2 and a rate for experiment 1. I'm going to have a K. In this case, it'll be the same no matter what. I'm going to have a concentration from my experiment 2 and a concentration from my experiment 1. You can see where I'm going with this. Oftentimes this is also written on all one line. So whereas I have this thing that looks like a bunch of little fractions, you can also see it written oftentimes in the book all as one. But realize that in this case, multiplication, it all works together. So now I get to plug in numbers. So my rate 2 is this 4.8 times 10 to the negative 3 divided by 1.2 times 10 to the negative 3 is equal to k. We still don't have a value for that. These are going to cancel because it's just a constant over a constant. Then I have my 0.1 divided by my 0.1. And even if we had done this first and these were both raised to the x power, that power is the same. So even though we solved for it first and we actually know that this is in fact 0.1 raised to the 1 and 0.1 raised to the 1, even if we didn't know that, it would still be a number raised to the exact same exponent. So this would actually also cancel and give us 1. Then my last component is going to be that amount of my chloride compound. So I've got 0.04 raised to some power I don't know, divided by the same thing, again, raised to a power I don't know. Oops. This needs to be a 1 for experiment 1. So yes, I am trying to copy this data from up here. Now notice that experiment 2 has to be on top the entire time. So my 4.8 is on top here, my 0.04 is on top here. My 1.2 is down the bottom here, my 0.01 is on the bottom here. So again, these have to match the entire time. So after I do this math, I should get 4 is equal to 4 raised to the power of y. Now, here is the part, again, where you may very well just know that anything raised to the power of 1 is itself. So in this case, y is equal to 1. You could do that by playing guess and check. You could plug it into your calculator and say, now I know what it is. The other thing you can do, which again, some people don't like, but you can do this, is you can actually take the log of both sides, and that would actually let you solve for y. But in general, if me saying the word logarithm makes you feel nervous, I would recommend that you play guess and check and figure out what will make this equal. So same game, at some point you should take a look and see what would happen if you had this 16 equals 4 raised to, we'll go ahead and give it the z power, and see what value of z it takes to make this equation true. That's essentially what we're doing here. So then in the end, want to make sure we actually finish this. So we want to make sure that we can write our rate law. So we're going to have our rate is equal to k times concentration of 1 raised to the 1 power, the concentration of our other reactant also raised to the 1 power. In general, raising things to the 1 power, since it is just itself, you are going to see things written like this, where we do not actually include the 1. It's there, but everybody knows it's there. So this is going to be our final answer.